In this video, we're going to graph a hyperbola. In your packet, please go to page 5, number 1. This is a very basic hyperbola. It hasn't even been shifted from the origin, as you can see from its equation. It's just y squared and x squared. It's not y minus or, y plus. So this is just going to be centered at the origin. Now, before we even get into that, though, we need to figure out if this hyperbola is vertical or horizontal. Now, the way that you figure that out is you look for the variable that comes first in the equation, because that variable is positive, okay? So it's not the variable that has a larger denominator, okay? It's the variable that comes first in the equation. So in this equation, the y squared comes first. So when that happens, we're dealing with a vertical hyperbola, which means that the wings or the branches are going to be opening up and down. So you're going to eventually have something that looks like this. All right, so in order for us to get that graph, though, we have a lot of work to do. First, we need to get our A, B, and C. So with a hyperbola, the first denominator, in other words, the denominator of the positive term, is always your A squared. So A squared is going to come first. So in this case, we have A squared equals 36, which means A is 6. And then 49 is going to be the B squared. So that's always going to come second. So B squared is 49. B is 7. And then to get C, for a hyperbola, it's the Pythagorean theorem that you're using. Now, this is different than an ellipse, because in an ellipse, the formula, it looks the same, but it has a minus. For a hyperbola, it has a plus. Okay, so we're going to go ahead and fill in 36 plus 49. So that's 85. So C is rad 85. And we'll talk about what each of these means in a few minutes. Okay. So now that we have that established, let's go through the information on the left-hand side. We'll go through each of those, and then we'll graph as we go along. Now, notice I drew the x and y axes already. For this particular problem, you can just center them, but the reason in this packet the axes are not drawn for you is sometimes you might have to, shift them a little bit to make the hyperbola fit. So you have to, before you start graphing, you really should look at your A and your B and your C and see how much room you're going to need. Okay, but in this case, you can just center them. Okay, so now the center of the hyperbola, like we said before, is just going to be 0, 0. There's no shift. Now, I just want to point something out. So go ahead and write that, and then I want to point something out on the side. In this case, it doesn't matter because it's 0, 0. But let's say you have something like this. Okay. So this is a hyperbola, but there is some shifting going on here. It's not centered at the origin. A common mistake is, when asked to identify the center, a common mistake is kids will say it's 1, -3, but it's not, because remember the x has to come first, so it's actually -3, +1 for this. That would be where the center is. So you have to make sure that you're putting the h first. The h is here because it's x minus h squared. And this is y minus k squared. So you have to make sure you're putting the h first. Okay, so that was just like a little side note It doesn't have to do with this problem, but for the future. All right. So let's, after you draw your axes, let's plot our center at 0, 0. Okay. Now, the next thing that we're going to do is we're going to find the vertices. So we have that our A value is 6, which means each vertex is 6 units away from the center. And we said that this is a vertical hyperbola. So we have to go up 6 and down 6 because it's vertical. So put a point and you can call that, just label it V. And actually we should label the center with a C. Okay. So now those vertices that we just drew, eventually we're going to draw the wings off of them. Okay, so that's eventually, but we can't do it yet. We're not ready to draw the wings yet. Okay, so the ordered pairs for those, it's just 0, 6 and 0, -6. Okay, the co-vertices, now we're going to go the other way. So we're going to go horizontally. It's 7, so you're just going to go 7 in each direction. Okay. Making the ordered pairs, 7, 0 and -7, 0. Okay. As far as the transverse axis, remember the transverse is the one that's connecting the vertices. So it's your main axis. So it's going to be, in this case, it's always going to be 2A. So it's going to be 12 here. You can count or you can just double the A. So I'm just going to make a note that it's 2A. So it's 2 times 6. So it's 12 units. Okay. The conjugate axis is the axis that has the co-vertices as its endpoints. So for that, same idea, you can do 2B if you want, or you can count. So it's 2 times 7 is 14. Now notice there's a difference here between this and the ellipse. With an ellipse, the major axis is always longer. But here, the transverse axis might not necessarily be longer. It's just the axis that the vertices are on and that the foci are going to be on, or they're going to be a little bit beyond it, but they're going to be on that, basically that line. Okay. Now that we have that drawn, the next thing that we need to do is we're going to make a rectangle. When you're making the rectangle, you're going to use the vertices and the co-vertices to kind of give you the dimensions of the rectangle, how wide, how long. So I'm just going to use a different color. Okay, and I'm going to make a rectangle. Now, the rectangle is technically not part of the hyperbola. It's just going to help you draw the hyperbola. So you're going to want to use dashed lines when you're drawing it. Okay, so I'm going to go as far to the left and right as the co-vertices, and I'm going to go as far up and down as the vertices. Okay, so there's my rectangle. Now, letter F says the equation of the asymptotes. So you're going to have two asymptotes, and they're going to go diagonally through the rectangle. They're going to go through the vertices of the rectangle, the corners of the rectangle, and they're going to go through the center. So if you have a straight edge, you could use it now. If you don't, you can eyeball it, but I think it would be better if you use a straight edge in the future. So let's draw them, and then we'll figure out the equations of them. Okay, so I'm going to pick a different color. I'll pick red. Okay, so what I'm going to do is I'm going to go from the center to this vertex. Now, be careful when I'm saying vertex now, I'm talking about the corner of the rectangle. So the asymptote is always going to go through the center, and it's going to go through the corners of the rectangle. So this is going to be one of my asymptotes. And go all the way to the end of the grid, because you're going to see these are important for when we're drawing the hyperbola. Okay, and then the other direction. And you put arrows. Okay, and then we're going to draw the other asymptote also. Ooh, you know what, I'm going to extend that a little bit. I don't have a straight edge on this thing, so it's a little bit of a problem. Okay, so we have these two lines now. We need to write the equation. So we're going to flash back to, I guess you learned this in Algebra 1, the equation of a line in point-slope form. So remember, when you're writing the equation of a line in point-slope form, it's actually very simple. So it's, the formula for it is y minus y1 equals m times x minus x1. And what you'd fill in is you have to fill in the slope and the x1 and the y1. Okay. And you don't even have to isolate y when you're done. You can just leave it like that. So this is the equation that you're going to use whenever you have to write the equation of the asymptotes. So again, it's called point-slope form if you didn't remember. Okay, now, this x1 and y1, we're always going to use the center for that point, because the center is always going to be on both asymptotes, so it's the easiest point to use. Now in this case, it's going to be 0, 0, so it's super easy. But even if it wasn't, you know, whatever the point is, you can easily plug it in. Okay, now the slope, what you would do is to find the slope of the asymptotes. The slope is going to be the same except one is positive, one is negative. What you do is I would just count the rise and the run. So you go from the center to one of the corners of the box and just count the rise and the run. So I'm just going to highlight it here. So we have 1, 2, 3, 4, 5, 6 going up. And then this is going to be 7. And the other one is going to have the same slope, but it'll be negative. So it's just going to be plus or minus 6 over 7. Now you might notice that the 6 was actually our A value, and the 7 was our B value. Whenever you have a vertical hyperbola like this, in order to get the slope, it's always going to be plus or minus A over B. So if you want to remember it, you can. I personally just get it right from the picture. With a horizontal hyperbola, it's just going to be flipped. It's going to be B over A. Okay, but you really just need to get it from the picture. All right, so now that we have everything, we can write the equation. Now remember, in this case, our center is 0, 0. So our equation is just going to be y minus 0, which is just y, equals, and instead of writing two equations, you can just do plus or minus 6 over 7. Okay, and then it would be parentheses x minus 0, but x minus 0 is just x, so I'm just going to leave it like this. If it wasn't x minus 0, you would have to use the parentheses. Okay, so that's the equation of the asymptotes. Okay, next, the foci. So the foci, similar to an ellipse where the foci were always on the major axis, the foci are always going to be on the transverse axis. I mean, a little further out, like technically the transverse ends at the vertices, but it'll be along that same, like imaginary line, basically. So in order to get the foci then, if you were dealing with a vertical hyperbola, then we have to go up and down. If it was horizontal, we would go left and right. So in this case, I'm going to graph it just to give you an idea, but normally you wouldn't have to graph it, but again, I'm just doing it so you have an idea. So rad 85 is your C. So the C is the distance from the center to each focus, okay, or focal point, sometimes it's called. So, well, what is rad 85? So 85, you have to think between what two perfect squares does 85 lie? It lies between 81 and 100. I have room here. Okay, so that means that rad 85 is between 9 and 10. Okay, so I'm just going to count like 9.5 boxes. Again, it's just to show you so you can see what it looks like. Somewhere around there. That's one focus. And then this is the other. Okay, so as far as the coordinates go, it's going to be, in this case, 0, and then it's going to be 0 plus rad 85, 0 minus rad 85. So we're manipulating the y coordinate because this is a vertical hyperbola. So for us, for these purposes, it's easy. It's just going to be 0, comma, so 0 plus rad 85 is just rad 85, and then 0 minus rad 85, oops, is negative rad 85, okay? If there was a number, let's say the center was 0, 2, then it would be 2 plus rad 85, 2 minus rad 85. That's all. Okay, now the focal chords are going to be perpendicular to the transverse axis. They're going to go through the foci. And the point of having the focal chords is, if we were going to be really precise about our picture, you would get the focal chord length and cut it in half, and then you would go left and right that distance, and that would give you like 2 extra points on the hyperbola, so your hyperbola would be more exact. We are not going to do that for this. We're just going to kind of eyeball the hyperbola, the curves. So in fact, let's do that now before we finish the rest of these. So let's go to each vertex. We have 2 vertices, and we're going to draw the wings of the hyperbola. Maybe I'll do it in a darker color. So the wings of the hyperbola have to approach the asymptotes. That's the point of them. So like the pictures that I drew up here originally, okay, our hyperbola is not going to look like that because look at these asymptotes. It has to be much wider than that. So if you watch what I'm doing, I'm going to start at the vertex, and I'm just going to draw a wing that gets really close to the asymptote, but doesn't touch it. And then same thing on the other side. Okay, so that's half, and then you go down here to the other vertex, and you do the same thing. Okay, so when you're drawing it, it needs to approach the asymptotes. Don't just draw a U. Okay, that's important. So now with that drawn, I'll just demonstrate for you the focal chords. They go through the foci perpendicular to the transverse. So they just go like this. So that's one focal chord, and this is the other. So if you did have if you were being very precise about your picture, you would first get the focal chord length and cut it in half, and then use that to help you plot the hyperbola. Okay, we're not being that precise, so you don't have to worry about it. As far as the focal chord length, letter H, it's the exact same formula as it was for an ellipse. So it's 2b squared over a. I don't have a lot of room, so I'll do it down here. So 2b squared over a. B squared is 49. A was 6. And actually, to make this easier to simplify, I would just do 2 goes into itself once, 2 goes into 6 3 times. So the focal chord length is 49 over 3. Okay. The eccentricity, just like it was for the ellipse, the formula is C over A. So that one I have room, so C over A. Rad 85 over 6. Okay. Now the eccentricity with a hyperbola is always going to be greater than 1. And the further away it is from 1, the more, like, the flatter the wings are, the more they approach the shape of a line. Okay, the further they are from 1. If they're more inward, like these ones that I drew here, okay, these will be closer to 1. They'll have a smaller eccentricity. All right, domain. So in this hyperbola, the hyperbola goes to the left forever and it goes to the right forever. You can see the arrows. So it's just going to be all real numbers for the domain. Okay? Negative to positive infinity. It's easiest to do this in interval notation. Okay? Just like we did with the ellipse. Now the ellipse was easier because it was a starting number and an ending number. This is different, but it is still easier to use interval. Okay, for the range is not all real. Although it goes down forever and up forever, there's a whole section in the middle that's not part of the hyperbola. All these dotted lines, they're not actually part of the hyperbola. Okay, they're just the axes to help you draw the hyperbola. So for the range, there's going to be a U in the middle, which would account for that space. So for the range, you go low to high. So low, we are starting at negative infinity. And then we're stopping here at the vertex. So that was negative 6. U. And then it picks up again at positive 6 and it goes up to infinity. So with a hyperbola, either the domain or range, one of them will always be all reals. The other one will have that U in the middle. Okay? So this is a lot of information, but if you draw connections to the ellipse, it's really not that bad. It's very important that you know the formulas, that you know the vocabulary, and also that you're just very meticulous when you're drawing it, and that you don't try to just jump the gun. Like, take your time and do every single step. Okay, if you need to, you can watch this again to help you. I will be making another video also. Okay, have a good day.